this is a video of assignment 3, and this is my student ID, and I type my student ID for the code and I run the code. As you can see, there's a list of questions and in quiz, and here is it. And I selected quiz 5, question 3, quiz 9, and quiz 8. First, I want to introduce quiz 5, question 3. To introduce decision trees. A decision tree is a tree structure in which each internal node, and as you can see, the red one is internal node, represent a judgment on an attribute. Each branch represents the output or judgment, and finally the leaf node, which is the green one, represents a classification result. The classification of a decision tree is based on a calculation of the entropy value and the resulting information gain to determine which value or attribute to select as a node. Therefore, there's no necessary relationship between the number of nodes and the number of training sample. As Professor Yu mentioned in lecture, there could be a million sample, 10 million sample, 10 sample, all the same. We use the same set of rules, so the number of rules. As mentioned above, the nodes of a decision tree are created and selected by comparing the information gain of the features and selecting the features that increase the information gain as node. Therefore, the number of nodes and the attributes of decision tree are not necessarily equal. In the third option, the construction of the decision tree replies a sample of training data. But when tree is constructed, the training sample is no longer needed. The initial training samples are not needed when the problem is predicted using other data. The last choice, the leaf node, is the last layer of nodes, which means that the decision tree has completed all the classification. Each non-leaf node in the decision tree records which features were used to determine the category, and each leaf node represents the final category. Second question, we can take a look at this picture on the right. So here is the forward power equations for the neural network. If we just get rid of this, get rid of function g, and set 1 equals z1. Alternatively, I could say that g of z is equal to z. Sometimes this is called linear. We can see the computation here. Finally, the neural network is just outputting a linear function. Neural networks with a lot of hidden layers and a lot of layers. It turns out that no matter how many layers neural networks have, if I just use linear activation functions, or alternatively, if I don't have activation functions, then no matter how many layers neural networks has, always doing is just computing a linear activation function. So I might as well not have any hidden layers. Therefore, even I go deeper into the neural network, I'm not computing more interesting function unless I introduce non-linearity. We just use a non-linear activation function inside the hidden layers in a neural network. This is because we need to introduce a non-linearity to network to learn complex patterns. Without non-linear activation functions, a neural network with many hidden layers will become a giant linear regression model that is useless for learning complex patterns from real-world data. The performance of a neural network model will vary significantly depending on the type of activation function we used inside the hidden layer. So we choose this one. A voting ensemble or majority voting ensemble is an ensemble machine learning model that combines the prediction from multiple other models. The minority obeys majority. Now we have 3 independent binary classifier. According to the majority rule, Well, when all three binary classifiers are wrong or two of them are wrong, the final prediction result will be wrong. We can see the formula for the actual calculation. To make it clear, I want to use Google Sheet to list all the permutations. As you can see here, we can look at the sheet as in the title. Each of classifier has a 20% probability being wrong, so here's 20% and the correct probability is 80%. We can see that all wrong are based on the this sheet, as you can see, and all correct. Then I list, as you can see, I list all probability permutations, a total of 8, by multiplying the probability that each classifier is wrong or correct. The probability of that combination or Q is obtained, and combination with 2 or more wrong are added, as you can see, added, resulting in a final result of 10.4%. As you can see, so we choose this result.